And the basic message is there is no necessary conflict. It's the same message we heard this morning from His Holiness, from Arthur, between Buddha's philosophy and scientific procedure, because both are committed to systematic processes for getting at approximations of the truth with a clear understanding that there's always the possibility around the corner that some new evidence will arise that will challenge something you believe. Einstein was famous for having said, "No experiment will ever prove me right. A single experiment can always prove me wrong." And there's a kind of commonality of approach and belief in that. It was a beautiful statement. Thank you very much. Your Holiness, is there anything you would like to say to your brilliant student colleague in response to this presentation, and then we'll move along.
Gave an explanation particularly about the mode of inquiry, the way we seek truth, and this is very important. So in terms of the consciousness, various explanations of the consciousness, we have the Abhidharma system. We also have a tantric system where various levels of subtlety of consciousness are spoken about. In the tantric text, they talk about the necessity for straight physical postures, in order to have a clear and straight concentration or thought. If your physical posture is straight, then the channels are straightened and the wind flows smoothly, and as such, your mind would be clear and so on. So last year I remarked about this. Paul Ekman spoke about 16 different mental factors that are connected with anger that could be perceived on one's facial expression. In the lower Buddhist school of thoughts, 51 mental factors are spoken of. However, in those mental factors, there are many. There are many mental factors that are spoken in the tantric texts that are not explained in the lower school.
Yes, Your Holiness. We have gone over time a little bit, but this has been a very, very fruitful conversation. I'm struck you are constantly generating these questions that are extremely interesting research questions, and it reinforces your interest in education, because we need to educate many people who can work on these questions you keep producing. We need a whole army of investigators. Thank you. Thank you.
Thank you.
And Jimpa, thank you very much.
Perhaps one joke I would like to mention, to express. Now I retired from political responsibility, so perhaps I may join the group of researchers.
You are very welcome, always. You make yourself a guinea pig? Control your dreams?
Yes, if highly necessary, then of course. what is the past experience? One practitioner, see, although he did not sort of specifically sort of because of that train about the inner heat. Tumu. No, Dr. Benson or something,
Herbert Benson.
Howard Benson. He actually brought to America and some kind of sort of experiment. Then the room where they carrying the experiment, very cold. So eventually that really causing some illness, that practitioner. So I do not want to become like that. But fortunately, this guinea pig survived. No other problem, no side problem.
Healthy.
Healthy guinea pig. Yes, now next.
Thank you very much. So next we will hear again from Arthur Zients. We'll change seats. And he will be making a presentation on quantum physics. So continuing in many ways where we left off this morning with his brief talk. And giving us a kind of overview of this field and where it has come from and where it is now and how to think about it, this field of quantum physics, which is radically different from traditional physics.
Testing, 1, 2, 3. Can you hear me? Testing, 1, 2, 3. A little bit louder. There you go. Okay.
How was the translation?
Your Holiness, before we move on to quantum physics, I'd like to speak a little more about Galileo. Because Galileo not only looked at the moon and the planets and so forth, but he also was a student of nature on the earth, the experiments on the earth. And I'd like to speak about one very important experiment, one which also became part of Albert Einstein's general theory of relativity. And I would like to do this because Galileo uses reason. In some sense, purely reason. Is it possible to gain insight into the world purely on the basis of thought? And here we see an example of his reasoning in a way that is like your reasoning and the reasoning of so many here, highly disciplined, very careful, leading to conclusions that then one can test experimentally, but in thought, they are predicted purely on the basis of reasoning. Einstein was also such a figure who loved to think. I'm going to do, it's a little hard to see on the screen over here. Can you pull it up on the screens to the left and to the right? But I'm going to demonstrate. Can you hand me one of those candies? Thank you, Crystal. So I have two objects here. One is heavy and the other is light. This is very light, this is very heavy. I'm not going to do the experiment. I'm going to have you think about the experiment, namely if I were to drop these two. And the question is, how would they travel? Would one go fast and the other slow? Would they travel at the same speed? What will happen? And can one, through thought alone, determine and predict what will happen? So I'm going to show it on the screen here. One possibility is that the big one goes fast and the little one goes slow. Another possibility would be for the two to fall at the same rate. Right? Now, I could take a vote and try to see what you think, will they go at the same rate, or will the little one go slow and the big one go fast because it's so heavy? All right, you all have made up your minds? Okay, now we're going to do a thought experiment. We're going to reason our way through this just the way Galileo did. He's going to say, let's take these two objects, the candy and the bottle, and we'll tie them together and make a third object, one which is the sum of the two, all right? Which is heavier still. It's heavier than each of the two. Will it travel faster still, or will it travel at the same rate? You tie them together, right? So then you have one object, but is now still more massive, still heavier. And you might think it will travel faster. But what if you take a string, a very thin string, a very, very thin string, and you tie the two together really very, very thin? Do you have one large object, or do you have two objects tied with a string? Will the light one, which falls slowly, slow down the big one? Or will they be treated as a single object and fall quickly? You see? And he thought to himself, this is a kind of contradiction. The only way to avoid the contradiction is for them both to fall at exactly the same rate. And so he predicted...
So can you so?
Okay, so what will happen is the two, one could fall fast and the other slow. You put them on top, you tie them together, you have one object that falls very fast. Or you take a thread, very thin, and you have now a light object and a heavy object. The heavy object falls fast, but the light one falls slow, and so it pulls and slows down the heavy object.
So if the weight difference between the two is big, then the string might snap.
Yes.
But
that's...
Then something's wrong.
Then something's wrong, right? So that's not the case. You could say, you take the two, you tie them together a little less, you tie them together a little less. When do you have two objects, and when do you have one object? You see the contradiction?
Yeah.
With two objects, you might expect the heavy to go fast. With one object, it goes very fast, right? But now you take this one object and you make it back into two objects step by step. What will happen? And so Galileo predicted, he said, the only way to get a consistent answer is for the small object and the large object to fall at exactly the same speed. No matter how light this is, this could be a grain of sand, and this could be a very big stone. You let them go, they have to fall at the same rate. Leaving aside air resistance, which we're going to do.
So what about if you do the experiment in an airtight chamber?
Yes, if you do the experiment, here's the experiment. The cats and the dogs run away. He describes
the Tower of Pisa.
Yes, the Leaning Tower of Pisa. He describes this experiment of taking something light, something heavy, dropping them, and they arrive at the bottom at almost the same time. And the question of air is a problem. If there's air, then this doesn't work so well. If we take a Kleenex and drop it, it'll...
Yes, that's right.
But if we do this experiment on the moon...
That's right now.
If you do this experiment on the moon, there's no air on the moon.
That's right.
And I have a film of this experiment being done.
But you cannot say no air.
Very, very
I
little
mean,
air.
you cannot say there is no air because there might not be the air that we are used to. But
Well,
there's
if you
no-
go there, which we've gone there, right? We've traveled there by spaceship, and you see up here is a image. See the images on the side. Here you have.
So, for example, on the moon, if there is no air of some kind according to its own local kind of laws, how would you explain the emergence of these mountains?
Yes, but that is due to the heat in the center of the Earth.
Geology.
Geology.
It's geology, heat in the center of the Earth,
So,
and that comes through two factors. One is the pressure.
that's
When
right.
you squeeze something,
So
very,
on moon
very
also that.
also on the moon, it becomes very hot. And then you also have impact
Yes.
craters, right, into the surface, which then throws up huge amounts of soil and rock. And you saw those craters through the telescope, those round shapes,
right.
right? In the middle of this, you'll find a huge stone has come out of the sky or out of the
Just a
space.
moving side and on normal way.
So, but there is some element of, some kind of atmospheric kind of, that allows the ability to move.
No, you don't need atmosphere to move. Yeah, you can, and at least from the standpoint of modern science, you need just space. You don't need anything in the space. It can be completely empty.
Yeah. His Holiness is referring back to the Buddhist, physical theory, which postulates that the ultimate constituents of matter are really understood in terms of the four elements, which are really seen more as potentials rather than, but the potentials that allow matter to be solid, to have cohesion, which is the water element.
주에 간다 소리 패지 아주 소리 세도 켜 놓고 해요.
말에다 간디 솔리 연구해야 돼.
영향 쌓여죠. 터주고
This
죠.
is now. So it's the potential that makes it possible for material objects to have solidity. So that's the earth element. The potential that allows for the possibility of material phenomena, objects to have cohesion, like kind of unity. That's water element, and so on. So they're really understood at a fundamental level, more like potentials. But His Holiness is wondering, so how would that theory apply to the moon if there is no air and no movement?
Yes.
So from that level of very, very subtle air must be there. Otherwise it's difficult.
Well,
Can one perhaps resolve the debate by saying there isn't enough air to breathe? So there might be a little bit of air, but there's not enough air to breathe, and the people there
that's
have
not
spent
air.
a
Yeah,
lot of
yeah,
air
yeah.
with
That's
them.
right.
Yeah, that's fine.
That's right.
Yeah, that's
That's
fine.
right.
And that's all what you need for your purpose.
yes, so if you're in intergalactic space, you're in deep space, there's always a little tiny bit of air.
That's yours.
And other matter, not just air. Air is a very particular kind of gas, a very particular kind of substance. But there are many others, but they're very, very, very thin. Yeah? And what they're thin enough is if you take a feather or you take a piece of Kleenex, right, and you drop it in the air, it floats. If you take the same Kleenex and you drop it on the moon, it drops like a stone. And I have a movie of this that was taken in 1971 when the US sent the astronaut David Scott to the moon with a friend who had a video camera, and they drop a hammer, very heavy, and a falcon feather. All right, the feather of a bird.
That's right.
Yeah, they're going to drop them, and you can see when they hit the ground. So if you'll watch the screen, I don't know if I can get the sound to work on this or not, but we'll try. Can the sound be turned up on my feed that's coming from the computer back there? I don't know if you have that together or not.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Did you notice how they hit the ground at the same time?
Gravity 지구로
지그지가.
Galileo was correct.
아니 애매해서.
Now watch them as they walk. See how they walk? They bounce around very slowly.
That's right. That's right.
Because the moon is so small that the gravity is very weak. And the things that they drop fall slowly, and they themselves weigh very little. Right? Do you want to see that again?
No, it's okay.
It's okay.
His Holiness is asking the Buddhist colleagues in the Buddhist Abhidhamma taxonomy, the quality of lightness is categorized as belonging to tactility, tactile property, and touch. And same thing goes for weight, heaviness.
Connected to the sense of touch.
Yes. So His Holiness is wondering why that is the case. So he's asking the monastic colleagues.
I'm glad he's asking them and not me.
야구시 먹주로마다 걔들 나비다. 아주 가르치기 나서. 제 삼다고 알았어요. 그냥 세르고 계시기입니다.
His Holiness said that Jimpa did not translate it accurately. He wasn't asking the scientist, but he was saying, what would we say? The Buddhists.
What would we, the Buddhists, say? Yes.
So this is just a fact. We
It's
can
a fact,
see
yeah.
like that. So it's all because of
Gravity.
자상가 양어도 지었어야 디 그걸 가서 영 지스코에 가는 하나만 샤메베 영서샤도 그때들 레저라셔야 돼. 가서 온다고이나 sometimes.
So His Holiness was saying that what this seems to imply is that actually the property of heaviness and lightness, seem to be again contextual. Judging by this, we cannot accept them as intrinsic properties of the things.
That's very, very important.
제가 어디를 설명해. 어서 배자도 대상당국이. 어서 배자나 셔셔 다른데 잡아게 맞죠. 나도 시야 되고. 대마셔 인지비 잡아치고.
So the Buddhist scholars, particularly the scholars, should not just rest at ease from the statements found in the text, but actually should subject them to inquiry further to try to see what was the underlying reasons for making such and such statement or attribution.
생야마다 파르드니 중에 템버리 기시랍된이야. 다딘 다가르다스 답자르다스 기시랍된 이마십시오. 리르고 수도 아주 보면 좋았어.
In fact, when there was a landing of the moon, His Holiness showed a photograph of the landing of the moon to one of the monastic colleagues by the name of Gishiraptin in Dharamsala. And, he said maybe they ended up landing somewhere in the corner of Mount Meru. So, for example, if one is that dogmatic and, kind of obstinate, then it would be very difficult.
Yes. Well, this is an experiment I wish Your Holiness could make. You looked at the moon when you were 10. Maybe now that you're a little older, you travel to the moon on the next station. Yeah.
Yes.
So this equivalence, this fact that the two drop really at exactly the same speed, exactly the same rate of acceleration, we call it, has very, very widespread consequences, and it's all the way into the modern physics, into the work of Albert Einstein, who likewise thought deeply about exactly this same issue. And from his reflections on this experiment, he came to the idea of his so-called general theory of relativity, his most profound contribution to physics, which really helps us to understand the largest aspects of the cosmos, the stars, the galaxies, and all of the rest. And this is from pure thought. Einstein did no experiments. He thought consistently. The way he characterized his thinking about this was what he said was his happiest thought, namely of falling out of a chair. Where you
Right.
fall out of a chair, you become the bottle that's falling, and you ask, what is gravity? Is it different than acceleration? And he came to the insight that these two things, gravity, which pulls us down, and acceleration, which speeds us up, have a very, very intimate relationship. They are, in some sense, the same. So this is Galileo to Einstein. The power of human thought is extraordinary. So in some ways, you already have the laboratory. You have the laboratory
Yes.
right here, and you've been working with it for centuries. And it is powerful in ways which, even in the physical world, can be demonstrated and proved by these experiments. I wanted to end, you've already seen some of these pictures, so I'm going to skip those. And what I'm going to do is speak just for a few minutes about another aspect of physics. You talked about the elements of the Buddhist way of thinking, the Buddhist thought. You probably know that in the ancient Greeks here in the West, they likewise had 4 elements:
Right.
earth, water, air, and fire. Plato saw them actually as geometric forms, but we won't go into that. In modern science, we usually take the stance that we should look ever more precisely, ever more exactly at smaller and smaller aspects of the things which constitute our world. So we look through a lens, the kind of lens that you might have in your reading glasses, and we see the object somewhat larger. You can take that same principle and create a microscope that's on the right, and the microscope makes what you see very much larger. So for example, if you take a leaf and then look through the leaf, you see on the right-hand side the magnification of the leaf cells, and then if you'd make it still larger, you can get the molecular structure of cellulose, and then you go into the actual components of that molecular structure and you find the atoms out of which that molecule is made. You can discover that there are about 100 of these primary elements. Each one has its own character. Some are gas, some are liquids like mercury, some are solids, some are explosive, some are non-reactive.
Lare.
완전 중원세 디간 리그도 중원 처음 펴지 않는데 이 전부 디간.
And they're grouped here in a way where the common properties are all in the same region. So this is a kind of map, if you will, of all of the ingredients that make up our universe.
디간다 라타 말로.
가.
디간다 라타 말로.
가.
디간 샤베나 라타 말로.
맞아 되게 중원 시시하송아.
말한저 중앙 시세 저러 봐.
맞아 뭐 하는 거게.
그래도
다들 봐시고 사서 차 단나 다들 제거지사. 그래서
잘라서 저래.
디 되게 중원 아버지 중원 시부터 뒤로래.
So Arthur, what would you say is the relationship between the elements table versus the Greek conception of the 4 elements? Or completely two distinct?
Well, they're distinct, but the perception of earth, water, air, and fire as components of the universe is very important. We would call them the states of matter, the first 3: solid, liquid, and gas.
Yeah.
Exactly the same.
Yeah, exactly the same.
So what is the relationship between the period
Then
table elements?
the relationship is that some of these here are solids. Some, for example, in this region in the middle, the ones at the ends, you can see, well, you can't see it very well, but these are all gases, for example. Certain ones are metals or a particular type of solid. And they're put together here with these different colors to indicate their kind of families.
그래, 약간
디 가서 애정 걸 버려 들이 더 잘하는데.
Related.
so this in relation to, say, for example, atoms, in terms of levels of reality.
grosser than atom.
This is grosser than atom.
Elements can be, for example, Here's what you would call the element of water. In our case, we would say it's a combination of hydrogen and oxygen
That's right.
together, and it's all water. It's all H2O. So you can have a lot of those atoms making up this volume, right?
The 주주 전문의
Inconceivably
받치죠.
many.
long.
So that each one of those elements there has a particular unique set of properties, you could say. You define each of these by its set of properties. Now we know that the properties which the chemists, the first chemists who came up with these different elements, we now understand this from the standpoint of still more subtle and smaller entities, electrons, protons, and neutrons, right? So you have the macroscopic world. It's analyzed into its elements. The elements each have a unique set of properties. Then you can go and explain those properties from the standpoint of the structure of the atoms themselves. And then you can explain the inner structure of the nucleus by still more. This would take us a few more hours to get sorted out. But it's a wonderful success, you could say, story, which also, however, raises deep philosophical questions. Because if you continue this goal and you ask yourself, can I see atoms? Are atoms in some way palpable? One way of doing this is not by any longer trying to use light. Light is too primitive, it's not fine enough. And so what one does...
근데 light 대표도 라우타고 그랬어. atom diet 나한테 재배나.
So what one does is, if you close your eyes and you feel something, you can tell its shape, even with your eyes closed.
Yes, that's right.
Yes? And if your finger is fine enough, it can feel the structure of your palm, your hand. And if you're trying to detect single atoms, then you need something which is extremely sharp, extremely pointed, very, very fine. And here in this diagram, you can see there's a tip. The tip is extremely fine, and then you bring it across a surface. The surface has a set of atoms, and then where it goes up and it goes down, you can make an image of this by computer, and you get the picture on the right. It's easier to see on these screens here. You see the picture on the right of the screen. It's produced by running
always
your...
moving one way.
Aren't the atoms constantly in motion?
Moving.
If they're cold and fixed to a solid,
Right.
you can actually get them to have very little motion. Yeah, but you're right. Mostly the atoms in this air, in our bodies, are constantly in motion. But as you cool them down, that motion becomes less and less.
Heat up to what? Beyond what temperature?
Heat produces the motion. Heat is, yeah.
So he's always wondering, in order for atoms to move, be in constant motion in their natural state, what level of heat would you need? I mean, how far you have to cool them down, in other words?
Yes, well, if you use Celsius, then you have to go 273 degrees is the end. That's
Below.
minus
Minus,
253. Minus
정말
15차는마도 그쪽으로 되겠어요.
서울 14이네.
So what about if it goes really hot?
There's
Then it's
no
con-
end to the really
I
hot.
see.
Right?
I see.
So in that case, for example, if we think of the atomic constituents of sun,
Of the sun.
of the sun, will that be the same in kind with the one that constitutes the earth?
The
Yes.
basic nature is same atom.
It's the same, but in another state because they're
Yeah.
so hot.
Yeah.
Right?
Nega,
It's the same basic material, but extremely hot. And in the surface, you have certain gases.
저상에는 상기 in atom 주제디 무시해도 거리가
요리요리도 잡으시죠. So that means the atoms are in constant motion up in the
Constant
sun.
motion,
Right.
yes, very
But
intense
slower.
motion. Fast
Yeah.
movement.
faster.
잡으시잖아. 조금씩 주고 봐.
알레 서울 있는 요거.
저거체. 장무시 차면은
Yeah. The surface of the sun, could be at like 6,000 degrees.
Yes.
And as you go in, it goes into many, many, many
Yes.
thousands of degrees hotter still. Yeah, so it becomes so hot that you have what we call a thermonuclear reaction. It's like with the hydrogen bomb.
Right. Right.
Inside the sun, we believe that the same processes are going on constantly on a vast scale, creating heat and light. Now, with all deference to my colleague Richie Davidson, who says his topics are very interesting, I think our physics is quite interesting too.
neuroscience the KJ or the Shuzon, the background, the physics the
Okay, now I have one last experiment. I don't know if you can see, but there's an arrow pointing to a person down at the bottom. That's a human being. And they're inside the Large Hadron Colliders. That's the detector for a single experiment, trying to determine the fundamental constituents of the universe. So you have a device, a piece of equipment that's larger than this building, and this is the equipment that's being used to do the experiments in our laboratories.
The atom collider.
This is a collider, yes.
Yeah.
This is right.
This is the most expensive scientific instrument ever built.
This is the most expensive scientific.
Where?
It's billions of
Where?
dollars.
Geneva.
Near
The
Geneva
one in
in
Geneva.
Switzerland.
CERN.
CERN.
I have been, yes. I've been there.
Yeah.
You've been there.
I think 73. There I learned the concept of quark.
Quarks.
Quark number 1, number 2, number 3.
Here are the quarks.
Then I think number 4th or 5th, not yet found.
Not
Now
yet
they-
discovered
So
at
since
that time.
then, I think now existing.
Everything has been discovered.
Almost 30 years has passed. So
Even the
any
Higgs
change?
boson has been discovered.
그래서
네, 단대 사업 때 Higgs boson 세드니요.
I'm going to end this talk in just a couple of minutes, but I want to end it with a very different set of pictures. In the Tibetan, keep going forward. Yes, that's right. Keep going forward in your... this is an image of the sky. You can see the night sky. If you wait and are patient, you'll notice that the stars move overhead if you go out each night. What are you seeing when you see that motion? Are you seeing the stars moving? Or are you seeing the earth move? Right? In fact, you're seeing the earth move, rotating. When the sun and the moon set, the earth is rotating. It looks one way, but we now understand it is another way. Now we've had a chance to travel with satellites and probes into the solar system. The picture at the bottom here is an actual photograph taken by this explorer here, this robot, of the landscape of Mars. This is the rocket which took it all the way to Mars, taking many years to get there. I'm sorry, here's the photograph of Mars. You can take also that same type of system in the Cassini satellite and go by Jupiter or Saturn and take photographs of this remarkable planets. And out of the cosmic exploration that we've had, both from the standpoint of theory and the standpoint of observation, we now have a much fuller and more adequate understanding of the universe. However, there are always new questions, and I want to just mention a couple. What we've discovered recently is that only 4% of the universe, that's less than a tenth, less than a 20th of the universe is made of normal matter, like this matter here. We don't know what the other matter is. We just know it can't be the same as the matter that we know. So 96%, most of the universe is either what we call dark matter or dark energy. Also tomorrow I'm going to talk to you specifically with Michel Bitbol about the mysteries of quantum mechanics.
Arthur, you might want to explain how
did we deduce that?
Yeah.
Sure.
Is it because of the gravity? that you cannot account for.
Yeah, so what you have are galaxies. Dark matter and dark energy are two different things. If you take a galaxy, which is billions of stars, yeah,
The galaxies,
a galaxy, yes,
billions of galaxies.
billions of stars, billions of
Right.
stars, and you watch it in its way in which it rotates, and you take what are the laws of physics and astronomy, and you count up all of the stars and estimate all of the mass in that galaxy, you find that it's too little. All of your calculations, your best estimates and observations is too small, so there is dark matter holding that galaxy together through gravity.
So compare that, much easier explain
Yeah,
here.
yeah.
Much closer.
Dark energy is a little harder. There you have to have supernovas, which are exploding stars.
Right.
And those exploding stars become like, we call them standard candles. They become a measure, they allow you to measure distances. And what we've found is that as opposed to the universe collapsing or slowing down, it's actually expanding at ever faster and faster rates. And so there must be a kind of anti-gravity, a substance which is an energy which, as it were, pushes things apart at very large scales, at very great distances. So you have in these two remarkable and recent discoveries, then the discovery of the vast majority of the universe, we don't know what it's made of. We don't know this new matter or the new energy. So there's still something left for us to do when we come back in our next incarnation. You can be the physicist, and I'll come to Drepung. Thank you very much, Your Holiness.